Calculus students. I apologize for my continued absence. Figured I would go ahead and provide you with a recording of today's lesson just in case it wasn't clear, simply going through the slides one at a time in class. This will also be the final lesson as we go towards a mid-unit test for Unit 4, so probably plan for that to occur on Monday in class. I'm not sure if I'll be able to return to school tomorrow in order to answer your questions. However, if you are struggling, please get in contact with me one way or another, either through my email address or through Edmodo. And if you're having problems with a particular problem, perhaps I can respond to it through a video or something to that effect. Anyway, today the final part of this first half of Unit 4 is going to be the limits of upper and lower sums. Our objectives for today is to find area by the limit definition. Student will demonstrate the ability to combine the limit definition and the squeeze theorem in order to calculate the area under a curve. And your essential question is, can I calculate the area under a curve? Okay. Now the last example from the last lesson, we saw that the area under the curve, and this was the particular curve and bounded area that we were looking at, and we determined that the area was somewhere in between the sums of these terms. Now, obviously, as the number of rectangles increased, you get closer and closer to the correct value of the actual area, and that is in response to the fact that the rectangles are actually covering more of the area underneath the curve, leaving less areas uncalculated, and not calculating so much of the area that is outside of the curve due to the rectangles extending beyond the boundaries of the curve itself. The drill here would be as the number of rectangles goes to infinity, basically suggesting that the width of each rectangle becomes infinitesimally small. The lower and the upper limits will basically converge upon each other, and n will essentially, as n is becoming infinitely large, then that causes the two trail ratios in those sums from above, causes them to become infinitesimally small, essentially becoming 0, so the limit converges upon the constant of 2 2/3. Limits of upper and lower sums. Here is the textbook definition for the limit. Let your function be continuous and non-negative on the closed interval from a to b. The limits of the upper and lower sums as the number of rectangles approaches infinity exist and are equal, meaning we don't have any intervals that are any differing sizes from any of the other intervals. The limit as n goes to infinity of the lower sum is defined as the summation as I goes from 1 to n. And then you have the function resulting in the lower area multiplied by the change in x. Okay, so that's basically your calculation of your rectangle that we have been doing. And basically, that is, we're establishing at this moment that this limit will be equal to an identical limit calculating the upper sum. And there basically you go. So instead of having two different definitions, one defining the lower sum and one defining the upper sum, as n goes to infinity, the sums approach each other until, in fact, they become equal to each other. Now, since the limit is the same from both sides, coming from both directions as we close in from the undersized area and the uppersized area, or the oversized area, pardon me, this is what follows the squeeze theorem. Now, I can't recall if we even took time to talk about the squeeze theorem earlier this year, but if you've heard it before, you'd understand that this is one of the stupider theorems in the history of all of mathematics. Basically says if you have three functions that are traveling through a graph, and the function that is the uppermost of the functions, meaning the higher up in the graph, and the function that is the lowermost of the functions, meaning the one that's the lowest in the graph, if the upper function and the lower function basically make contact with each other and coexist in the graph, at least for a moment, then the squeeze theorem guarantees that the function that was caught in the middle also shares that same point of intersection. So not real rocket science there to basically say if the highest function and the lowest function touch, then the function that was in the middle is caught in between them at exactly the same place. But this is the same idea from this limit process that the squeeze theorem shared to begin with. Okay, so let's look at the definition of the area of a region in a plane. Okay, let f be continuous and non-negative on the closed interval from a to b, just like we started off with the limit from above. The area of the region bounded by the function and the x-axis and the lines x equals a and x equals b. So basically these four constraints have essentially defined an area from above and from both of the sides and from below, so essentially kind of north, south, east, and west barriers on this function. The area is equal to the limit as n goes to infinity of the summation as I goes from 1 to n of the function itself times the change in the width of the rectangles. Okay, so essentially looking at a graph, what we are doing here is, of course, we have our boundaries. Okay, and then we have arbitrary rectangles that travel through our bounded region. We have a lower boundary, which we have typically come to define as the I-1 boundary. And of course we have the upper side of the rectangle, which is typically the I boundary. Okay, and somewhere in between there will be the actual value of x for the rectangle, which we are calling C. And of course, where this line intersects the function, you have the function evaluated at C sub I. And that is essentially what we are looking at, the squeeze theorem, as x sub I minus 1 and x sub I approach each other in the domain, then the value C sub I is caught between them. So essentially, when the two x values bordering this rectangle converge, C is caught in between them and basically becomes the overall height of where x sub I minus 1 and x sub I coexist. So there's the squeeze theorem and the limits of the upper and lower sums theorem kind of operating in conjunction with each other. Okay, so let's take a look at one here. Find the area of the following region by the limit definition. Our bounds are going to be the function of the parent cubic function, also the x-axis, and the domain bounds of x equals 0 and x equals positive 1. Okay, not necessary to have a graph, but until we get a grip on it, a little visual couldn't hurt. Okay, so obviously with these boundary constraints, we are restricted to quadrant 1. The cubic function will come through the origin and bend upwards rapidly towards infinity in quadrant 1. And of course, the rest of the boundaries are the x-axis and the y-axis in this case, and also x equals 1. So our bounded region must be this little tan orange area that just appeared on your video. Okay, so fitting the qualifications here, the function is continuous and it is non-negative within the closed interval from 0 to positive 1. We can choose any point that we want, so we choose an arbitrary point, setting c sub I equal to I divided by n for n subintervals. That being the case, the area is going to be defined as the limit as n goes to infinity of the summation as I goes from 1 to n of the function evaluated at c sub I times the width of the rectangle delta x. Okay, so there's the equation that we are working with. Okay, so doing a little bit of substitution here, we know that, of course, our limit is going to go from n to infinity eventually. The summation is going as I goes from 1 to n. And our function was the parent cubic function, so it's x cubed. So essentially what we're doing is we are replacing inside of our function with I sub n cubed times the width of the interval of 1 over n. Okay, combining some terminology here, we have I cubed over n to the 4th. Okay, now n to the 4th is constant, so it does really not need to be messing around with our summation. So I'm going to pull that n to the 4th out of the denominator and move it out in front of the summation, which leaves the summation to go from I to n of I cubed. Now hopefully you recognize that I cubed on a summation going from 1 to n is an identity. And that identity is n squared times n plus 1 quantity squared over 4. So that takes care of the summation. Now obviously we have a lot of terms here, and our experience should tell us that as n goes to infinity, it's going to wipe out some of these terms. So what we're going to want to do is we're going to want to combine this n to the 4th back into the denominator of whatever this other ratio is doing, and then separate the terms so as n goes to infinity, it does not wipe out the entire ratio. Okay, so doing a little bit of algebra, we end up with a constant 1/4. We're going to end up with a ratio that n is going to mess with as it goes to infinity of 1 over 2 to the n, and then of course another ratio 1 over 4n squared. Now as n goes to infinity, obviously both of the trail ratios in this little trinomial are going to become infinitesimally small, ultimately going to 0, which will leave the constant 1/4. And that is your area underneath that curve within those boundaries. Let's try again. Find the area of the following region by the limit definition. This time we're going to be bounded by a rather wide parabola that has a vertical shift of 5 and is upside down. And once again, we're going to be restricted within the first quadrant, but not the entire first quadrant. We're going to be restricted by the bounds in the domain from x equals 1 to x equals positive 4, as well as the x-axis. So that's going to keep us in quadrant 1. Here's what your graph looks like in case you are curious. Okay, there is the parabola. Again, it was vertical shifted 5 units, so it's up at positive 5. It is upside down, so it's traveling downward rather than upward. And we're going to restrict it from 1 to 4 on the x-axis as well as the x-axis. So that's going to be our area that we're actually looking for shown there. Okay. The function is continuous and non-negative within those specifications, so we can proceed by the limit definition. We can choose any point that we want. Okay, so in this case, if we have an arbitrary point, we cannot just use I over n this time, because we got to get that phase shift in there. So we're going to add 1. That'll move us over to +1 on the x-axis, and then we have 3 units worth of width to our region. So 3 times I over n. That should take care of all of our subintervals traveling from 1 to 4. Okay, so again, there is our limit definition. The area is going to equal the limit as n goes to infinity of the summation as I goes from 1 to n of f of c sub I times delta x. Okay, so here we go. The function 5 minus 1/5 of 1 plus 3i over n, plugging into our original function, squared. And that's going to be multiplied by the width of our interval, which is 3 units, divided by n subintervals. Okay. Simplifying that mess inside of the square brackets, we end up with a trinomial 24/5 minus 6i over 5n minus 9i squared over 5n squared. Now we're in a little bit better position to decide what is really happening with this summation. Okay, well, the constant on the end, 3 over n, was not a constant, but it's not going to be affected by the summation. So 3 over n can be pulled to the front of the summation, and then we'd probably be best off to look at each of the terms individually as a series of summations being added or subtracted. Okay, so that's what I have done. And actually, I've got a little bit of a notation difference there now that I look at it. The 3 sub n that is showing up there should actually be in front of the those parentheses, as the 3 over n does affect all of the terms, not just the lead term. So if you would move that set of parentheses, let's see if I can grab it and move it, and I cannot. I'll give you at least one example before this goes. These parentheses should have been there. And yeah, that's not going to work real well. There we go. That line should look like that, and as soon as I flip to the next slide, it's going to revert. But the 3 over n should affect all of the summations. Oh, no, it shouldn't. I just convinced myself wrong. This is what happens when I do calculus on medication. The 3 over n is on all 3 of the summations, but there were other terms that were factored out in each of the summations, and that that's why they don't look the same. So on the center term there, the 18 over 5 times n squared, the 3 was in the numerator, the n is in the denominator, but also a 6 factored out in the numerator to make it 18, and then a 5n factored out in the denominator to make it 5n squared. So I momentarily convinced myself I was wrong when I wasn't. Anyway, moving forward. Okay, the first term there, you have the summation as n goes from 1 to, or I goes from 1 to n of 24/5. Well, of course, that is just a constant, so it can be, the 24/5 can be simply moved forward. And the rest of the terms, you've got the summation of I as I goes from 1 to n of I, that is an identity. And then you have on the trail term the summation as I goes from 1 to n of I squared. That is an identity as well. Applying those identities and then redistributing the constant, or not the constant, but the term that was not affected by the summation, redistributing it, we end up with these, that binomial and the trinomial that are shown there. Okay. Applying the limit as n goes to infinity, we lose 3 of the ratios that are involved. We are still left with the 72/5 and the 9/5, actually negative 9/5 from the center term, and then another negative 9/5 from the trail trinomial that was there. And simplifying that, we have 72 minus 9 minus 9. The denominator is already common, which was nice. And then we can simply simplify to 54/5. So our area is basically 10.8 square units underneath that curve. Okay, so hopefully that sheds a little light on everything. You've got page 264, number 45 to 47, and number 52. I apologize for my continued absence. I hope it's not putting undue strain on you as far as continuing on with your academics. Haven't heard from anybody except for one person on one thing, and that was simply to request a video, which I did provide. If you're having problems, let me hear from you. So make sure we keep on task and on track, and be prepared for Monday's Unit 4, first half of Unit 4 test.